Hello and welcome to Armstrong's North American Learning Center. I'm John Bingaman, Educational Technical Director at Armstrong here in Three Rivers, Michigan. During our session, we're going to touch on 4 special topics for you. We'll touch on steam basics, steam trap operation, proper steam piping, and water hammer. Before we begin, let's take a little look at some other portions of our demonstration room that you won't be able to see today, but might be available to you for future training sessions. We have on our north wall an air handling unit with multiple forms of steam humidification, either direct steam injection or self-contained humidifiers, so we can demonstrate with variable control, see-through ductwork, absorption distance, and humidity control, either using steam or evaporative type devices. And then as we move toward the corner, we have a steam quality monitor. And this steam quality monitor has the ability to identify the dryness fraction of steam, the amount of superheat present when you drop the steam pressure to atmospheric pressure, as you might in a sterilizer or autoclave, any amount of non-condensable gases concentrated in the steam itself. As we continue to move here, I've got 2 steam flow meters, different technologies, and with a modulating control valve, and there's a variable flow, we can demonstrate and compare responsiveness to each of the technologies. As we move now toward our north wall, here we have a hot water temperature control system and the ability to vary the makeup of our zones, mixing hot and cold temperatures. We have 2 different forms of hot water temperature control valves. One, an EMEC type valve for industrial applications, another, the brain for institutional applications, as you might find in hospitality or in healthcare. Either one of these devices has the ability to maintain hot water temperatures plus or minus 1 degree Fahrenheit. As we move toward the corner, we have a steam trap testing demonstration here where we can demonstrate with traditional forms of steam trap testing through sight, sound, and temperature. Some of these steam traps are in good working order and some are failed. We can go through the different methods and show their strengths and weaknesses. And then finally, we have a glass low pressure trapping demonstration here, a glass heat exchanger with glass piping, glass bodied steam trap, and then piping where we can demonstrate either drainage with the benefit of gravity from the steam trap or going overhead, attempting to lift the condensate with a modulating control valve. For some of those applications where there's too much back pressure, we can also demonstrate what we call a double duty, a combination steam trap and mechanical pumping trap down here, lifting overhead using steam as the motive force. Alternatively, we also have a electric condensate pump here, and so we can demonstrate the benefits of mechanical versus electric condensate pumps. Well, for today's session, we're going to, again, touch on 4 topics: steam basics, steam trap operation, proper steam piping, and water hammer. And we'll begin talking about steam basics. So we know as we talk about steam, we'll be talking about British thermal units, BTUs. The amount of heat necessary to raise 1 pound of water through 1 degree Fahrenheit. That's a BTU. We'll be referring to 2 different forms of heat that comprise the total heat of steam, both sensible heat and latent heat. Sensible heat is the heat of saturated liquid, the heat we add to the liquid to bring us up to the boiling point at whatever pressure we're operating at. We call it sensible heat because we can sense or see the addition or subtraction of this heat with a temperature change. Latent heat is the active heat of steam, the heat of vaporization, Another word for latent is hidden heat, because as we add it or take it away, temperature does not change. Again, when we add the sensible to the latent heat, we get the total heat of steam. Now, we have a simple pot of water in our slide and 1 pound of liquid in the pot. As we raise our temperature from 32 degrees Fahrenheit to 212 degrees, we've added 180 degrees Fahrenheit. And thus, by definition, we've added 180 BTUs of sensible heat. So at this point, I have a pot of hot water at 212 degrees. It's an open pot at 0 pSig. Now, if I want to turn that 1 pound of hot water to a pound of steam, I'm going to require 970 BTUs of latent heat to do so. Now, with an open pot, clearly, if I add all that energy, I'm going to boil off my water. But it's going to take that much energy, 970 BTUs, to simply turn that 1 pound of 212 degree liquid to a pound of steam at 212 degrees, 0 pSig. Had I added half of that value of 970, 485 BTUs, I would then have half a pound of water and half a pound of steam. Well, let's look at a common pressure used in HVAC systems, 15 pSig. The steam table says that steam temperature will be 250 degrees Fahrenheit. 250 minus 32 degree starting point means I've added 218 BTUs of sensible heat to get to 250. So I have 1 pound of liquid now as I plunged my pot, 1 pound of liquid at 250 degrees in a 15-pound system. If I want to turn that 250 degree liquid to steam, I need 945 BTUs of latent heat. By adding that heat, I now have 1 pound of steam at 15 pSig, 250 degrees. So when we look at the steam table, across the top, I've got gauge pressure, temperature, and we'll be talking in degrees F. The sensible heat, or heat of saturated liquid, in the third column. The fourth column is my latent heat. And then the total heat of steam, the sum of columns 3 and 4, followed by specific value. And so if we take a look at 15 pSig, we said earlier that right off the steam table, we have 250 degrees. If you know pressure, you know temperature. If you know temperature, you know pressure, as we talk about saturated steam. We said earlier that I have 945 BTUs of latent heat with my 15-pound steam, and my specific volume of that steam at 15 pSig is 13.75 cubic feet per pound. Now let's look at a higher pressure. In our example, we have 100 pSig with a steam temperature of 338 degrees Fahrenheit. As I know pressure, I know temperature. Here, the pressure's gone up, and thus the temperature's gone up. But the latent heat goes down in BTUs per pound. At 100 pSig, I now have 880 BTUs of latent heat. And that trend continues. As steam pressures rise, the latent heat in BTUs per pound is reduced. And thus, all things being equal, low pressure steam is more efficient than higher pressure steam. If that's true, why do we use the higher pressure steam? Well, two real reasons. The first is that there are some processes that simply require hotter temperatures. And another is sometimes you need more pressure for distribution purposes to get the steam out to the points of use. So back to our steam table then, if we look at a specific volume, at 15 pSig, we said it was 13.75 cubic feet per pound, but 100 pSig is less than 4 cubic feet per pound. So I'm compressing that vapor, a smaller specific volume with higher pressure, and thus smaller size pipe at the higher pressures. Well, we can't talk about steam without talking about the presence of air and non-condensable gases in that steam. Where's the air come from? A couple of sources come to mind. One is as you shut down a steam system, you draw a vacuum and you draw air into the system. And another is the makeup water. Back in the boiler house, makeup water has minerals in it. And as we boil the water, those minerals take off in the form of CO2 gas with the steam. That's not an issue until we get into some low velocity areas or areas with potential short circuiting in places such as a shell of a shell-to-B exchanger. And let's take a look at an example here. We know that at 100 psi-G, my steam table says I should have 338 degrees Fahrenheit. Dalton's law of partial pressures, though, says that if I have by volume in a concentrated area 10% air, then my steam temperature will correspond not with 100 psi-G, but with 90 and be at 330 degrees Fahrenheit. Now, if you can have 10% by volume of air in a concentrated area, you can easily have 30%. And in fact, that gets to be a bigger issue because the more air present in that concentration, the lower my temperature. And so for an end user, for an operator with a heat exchanger or a process device, he may not sense the loss of 8 degrees with the presence of that air, but he probably will recognize the loss of 26 degrees here, so I drop down to 312 degrees with a 30% concentration at 100 psi-G. And what's he likely to do? To increase the pressure, more than likely, because he's looking at his pressure gauge, not recognizing the temperature's not there. The solution for that is the use of a properly located thermostatic air vent. Let's move on now and talk about flash steam. When condensate under pressure is exposed to a reduced pressure, some of that condensate is going to re-evaporate into what we call flash steam. And in our illustration here, we have condensate at P1 passing to and through a steam trap, discharging downstream. I have condensate, and some of that condensate is going to re-evaporate into flash. Now, flash steam is important for lots of reasons. One is it has all the characteristics of live steam at the reduced pressure. So it has the heat value, it has the chemicals that were invested at one time. It's important for that reason. And if you're sizing a condensate return line, you must size it anticipating the presence of the flash steam. Condensate return lines really are sized more for low pressure flash steam than for condensate itself. Additionally, if someone is trying to diagnose a steam trap, determine if it's working properly or not, and they see the flash steam, they may misdiagnose the trap, thinking it's live steam, the trap has failed. And so proper education becomes very, very important. Well, how much flash steam is formed? The percent of flash steam in BTUs per pound, right off the steam table, is simply the amount of sensible heat at the higher pressure minus sensibly the lower pressure, divided by latent heat at the lower pressure, times 100 gives you a percentage. And so if I have 100 psi-G steam, and I release my condensate to atmospheric pressure, I would have 13.3% flash. Let's move on now to steam trap operation. To do so, Mitchell Bingaman is going to come up and talk about how F&T traps and reverted bucket traps work. Mitchell Bingaman is an application engineer with Armstrong Steam and Condensate Group.
Right, so as John mentioned, I'll be covering how F&Ts, also known as flow and thermostatic traps, as well as inverted buckets operate. So we'll start with flow and thermostatics. Now, just looking at the name, you can tell there's two main components to this trap. There's the flow mechanism, and there's also the thermostatic element. Now, flow mechanism obviously has the float that'll be attached to a fixed pivot lever and a valve as well. And that valve and the seat will be at the bottom of the trap. And the thermostatic element is typically going to be a bellows, but it could be another type as well, like a wafer. Most time you'll see a bellows. And the best way to understand how a steam trap operates is to take a look at what happens on a system startup. So on a startup, you'll see air being pushed by cold water, being pushed by hot water or condensate, which is then being pushed by steam. So again, we'll start to see at first air and cold water entering the trap. The water is going to lift up the float, which will pull the valve off the seat, allowing the water to drain out through the orifice and go to the condensate return line. And that water level inside the body there has created a water seal over the valve. So because of that, the air and the steam won't be able to get to the valve. So on startup, we need something to vent the air out, and that's why we have that thermostatic element. So at this point, everything's relatively cool, so our bellows will be contracted, which means our valve's gonna be open, allowing the air to pass through and go to our discharge line. Then we'll start to see steam entering the trap. That's gonna heat up that element, causing it to expand and close off. So we're not venting any steam to our discharge line at this point. And over time, that steam in the body will start to condense from radiation heat losses. Eventually, it'll end up going out the orifice at the bottom. And eventually, you will get enough air accumulated to the point where it cools down that bellows enough to the point where it opens, allowing the air to escape. And then once it heats up again, it'll close off. And that'll just keep happening over and over. Now we'll switch over to a live demonstration of an F&T trap so you can see it. Okay, so we have our F&T trap right here. We have condensate coming in from the right, and it's going to be discharging out through our valve and seat at the bottom. We also have our thermostatic element up top here. And some of the main takeaways from this are that F&T traps don't back up condensate into the equipment that you're draining. So they're not going to flood any heat exchanger coils or anything like that. They're also a continuous drainer, so they don't have a regular cycle. So essentially, condensate is just going to come in and go right out. And that's important to know that they are a continuous drainer. If you're ever in the field testing them, or if you're trying to troubleshoot them, it's important to know that. Some of the main advantages of this trap are that it handles modulating pressures and varying loads very well, which is why it's our #1 recommended trap for heat exchanger applications, or really any application that has a modulating control valve. It also handles quite a bit of air too, because it has its own dedicated air vents as well. Some of the disadvantages are that the valve is at the bottom of the trap, so that means it's prone to clogging easier than other types of traps. So that's something to keep in mind. You might want to consider having a strainer installed beforehand to prevent that. Also, the float and the bellows are weak points in this trap, so either of them could be collapsed or ruptured from water hammer or freezing. If the float collapses, it's not going to be buoyant anymore, so the trap's going to fail to close because we're not able to discharge anything out of the orifice. If the bellows is ruptured, and that's typically what will fail first, then usually it fails open, so in that case, steam would be blowing through into our condensate return line. Okay, so that's pretty much F&Ts in a nutshell. We'll switch over to inverted buckets now. Okay, inverted buckets are another type of mechanical steam trap, just like F&Ts, and they're pretty similar to them. They also have a float, except now it's an open float and it's just an upside down bucket. And so that bucket is attached to a free floating lever, which also has the valve attached to it, and the valve and seat are located at the top of the trap now. Okay, so we'll look at this on startup again, just like with FNT. So we'll have air and cold water entering the trap. At this point, not much is going to happen. The bucket will stay at the bottom of the body, and the valve will slowly pull off of the seat. So we're discharging any air or cold water entering the trap. Then the steam's going to come up underneath the bucket, and that's going to give the bucket buoyancy and lift it up. Once the valve gets close to the seat, differential pressure is going to completely close it off. So at that point, we're not discharging anything. And for the trap to open again, we need that steam under the bucket to start condensing. And once enough has condensed and we lose some of our buoyancy, the weight of the bucket will be great enough to pull the valve off the seat, opening up the trap, just like you see here. So the trap is open, and we're discharging condensate again. And if you look closely, there's actually a slit on the top of the bucket in each of those images. And that's just representing a bucket vent hole. And that'll be in every single inverted bucket steam trap. And that bucket vent hole is really important because it allows air that's accumulated under the bucket to pass through it and collect at the top of the trap. And every time the trap opens, the air will also be discharged along with the condensate. And you will have some steam pass through there as well, but it's not going to be a lot. And there's actually a water level or condensate level right above the bucket, so that steam is just going to condense. So we're not actually losing any steam or any energy efficiency because of that. So let's switch over to the live steam trap again. We'll show the inverted bucket now. Okay, so we have condensate coming in from here and it's discharging out on this side. There's two main water levels in an operating inverted bucket. There's the one that's underneath the bucket, and remember this ratio of condensate to steam is going to determine whether the trap is open or closed. There's a second one, which I briefly just mentioned, at the top of the trap, and that's what we call the prime. And the prime is just essentially the body of water that allows the bucket to move freely up and down. And if we lose the prime, then the bucket loses stability and it won't be able to, the valve won't be able to properly seat and close off. So we'll end up failing open and blowing steam out to our return line. So some of the main advantages of this trap are that it's pretty rugged because it has an open float. And so it handles water hammer better than, say, an FNT trap. Another advantage is that the valve's at the top of the trap, so it doesn't clog as easily. Some of the main disadvantage is that you have to be careful when applying this trap on modulating pressure applications, because in that situation, if you don't have an internal check valve installed, you could have your prime get sucked out of the trap and thus causing it to fail open, as I just mentioned. Okay, and we have one more slide to show you, so we'll switch back to the presentation. Okay, so this is just a basic chart showing you the main characteristics for the most common types of steam traps. I'm not going to go into too much detail here, but if you wish to pause the video right now and take some notes, you're more than welcome to. Otherwise, I will pass it off to Cam Spence, who is our Director of Educational Development.
Okay, we're going to talk about steam piping, and you know, we pull up the first graphic here simply because as we look at a steam system and the piping that goes into it, you've got your steam distribution piping, you have your steam user piping. We're not going to go into that as deeply. We talk about more of the steam distribution piping portion of it. So a lot of this is common sense, and I think that you'll quickly recognize that, but we do give some rules of thumb or some harder data that you would want to follow in certain parts. But rules of thumb here, you certainly want to pitch piping in the direction of the flow. One thing to remember about distribution piping, gravity is always working for you along with the fact of your steam flow. That's helping to move condensate along as well. But you do want to pitch it. And so you want to pitch it in the direction of flow. That pitch would be about 1/4 inch per every 10 feet. Particularly, this rule would apply a lot when it comes to the process side of things, but it also works in the distribution side of things in longer runs. Whenever you take a branch line off from the main, always, always, always go off the top. Again, simple rule, gravity is working for you. When condensate forms, it's in the bottom of the pipe. So if you take the branch off the top of the pipe, gas being lighter, steam being the gas being lighter, you're going to be in that space, and that's where you'll want to be. Not off the side. You'll often hear someone say, well, if I just take it off the side, you don't want it off the side, always off the top. Use eccentric reducers as opposed to concentric reducers. Same reason. Water is in the bottom of the pipe. Concentric reducer will trap that water in the bottom of the pipe. Use the eccentrics. Insulate pipe. Again, might seem very obvious, but insulating pipe's very important. As steam's going through that is a place of heat exchange. If you don't have insulated pipe, that's going to condense. The steam that's in there, those water droplets will start to form, particularly in steam distribution. From not only an energy efficiency standpoint, it's important. Almost equally as important is a safety consideration. You do not want to have water hammer in steam distribution lines. Highly dangerous with the velocities that are there. Install thermostatic air vents. As you heard John talk about, air is always present, and we want to have the ability to evacuate as much air as possible. When that system is shut down and starts back up, it's full of air, and we have to evacuate that air. You don't want to have trapped pockets, and also air has other corrosive effects that you want to avoid. Installing drip traps, very important, and I think the obvious is that drip traps always go in the bottom of a pipe, and we'll talk about drip trap installations here in just a second. And then always install safety relief valves when and if required. Remember, relief valves are to protect the equipment downstream, and so that's its purpose. So pressure drops, you want to minimize the pressure drop to reduce both erosion and noise. And so some of the rules that come up is to not exceed more than a 20% supply pressure drop. When you talk about what that looks like in lengths of run, this question always comes up. If you stay between 2 to 5 psi drop per 100 foot of pipe, you'll stay safe. Velocities, and you want to minimize the velocities, again, water hammer and noise reduction, but some of the rules in heating systems, you can use lower velocities, 4,000 to 6,000 feet per minute are recommended. In process steam, that's going to pick up. If you stay between 6,000 and 12,000 feet per minute, you're in safe territory. Once you start to hit above 15,000 feet per minute, now there can be issues. And I think those are the things you want to avoid. When you look at traps and drip traps to go in distribution, the things that a trap needs to do, Mitchell had covered a few of those, but we want to get rid of condensate as soon as it forms. You want to be able to handle slugs of condensate. They need to withstand water hammer. Certainly there's going to be dirt, and those old systems, those are not pristine, clean looking inside that pipe. So you want to be able to handle the dirt and debris that could be in there. And if a trap fails open, particularly the steam distribution line, you want it to fail open. If it fails closed, you can have issues there with water backing up, and we're talking about water hammer again, which is going to be covered in the next section. Very, very dangerous. The best type of trap in drip applications for steam distribution are inverted buckets. Inverted buckets have that ability of those 4 main items above and getting rid of condensate as soon as it forms. And it's just a very durable trap in a difficult service. Drip legs. So the purpose of that drip leg is obviously you want to get the condensate out of that horizontal line and out of the way, and so it turns into a place where water can be stored, so then the trap can do its work. And drip legs are a critical piece, and the sizing of drip legs are important. So when we look at drip legs, again, always in the bottom of the pipe. Look at the top diagram. If that drip leg's too small because of the steam velocity going over the top, if it's too small, it may not go down into that smaller pipe. The other effect that can occur if velocity is going too high, it actually can pull water out of a pipe that's too small. It can actually siphon it out of there. And so down below, we show a properly sized drip leg, and we give you some rules of thumb to follow. And the easy one is it's the same size of pipe. If you've got a 1-inch pipe, you've got a 1-inch drip leg on up to 4-inch. 4-inch pipe, 4-inch drip leg. So it allows water to fall down in that pipe. Once you get above that, we do the nominal pipe size, half the size of the main above. So if you look at the rule that we give you off to the chart on the right, you can see up to 4 inch is a 4-inch drip leg. When you go to 6-inch, it's still a 4-inch drip leg, half or the nominal pipe size up. A 10-inch, again, half or the next pipe, nominal pipe size. Got a lot of 5-inch pipe out there, so it's 6. And so on. So it's half the diameter of the main above 4-inch. Again, adequate diameter to allow water to fall down into, to collect so the trap can do its job. And so some of the other rules in distribution piping, when you look at steam headers, if you've got multiple boilers, you'll want to use a drip or a drip trap on each, off from each of the end of that steam main header. A single trap, you'll pocket water on the other side and you'll get slugs. And so you'll want to have a trap on each side of that header. And just a quick rule there for the safety factor sizing, it's 1.5 times the boiler load times the carryover, which is, as a rule, is usually about 10%. And that's how you size those boiler header traps. So other trapping and distribution, figure 3 there, we show you a drip trap off from the bottom. And interestingly, as you see that drip leg come down, you'll notice at the end of that drip leg, we have a valve, and it's for a blowdown. As you can imagine, everything that falls down there is pretty nasty. You're going to get dirt, scale, and other things. And these are often called mud legs because it literally looks like mud that is down there. And so having a valve there to blow the dirt and garbage out of there so your trap doesn't have to handle it is a really good idea. Then you take off, you go to the trap, you can see we have an isolation valve. We then come to a strainer. The strainer also has a blow down valve because you want to be able to blow down strainers, and it goes to the trap. And the only thing we pictorially don't show here is that strainer would be laying horizontally as opposed to showing that strainer leg going down. We do that pictorially so that you can see it. We'd recommend laying the strainer on its side so it doesn't have a place necessarily to sit and collect. Head of control valves, for sure, we recommend that, and PRVs, we recommend that. But the same rule would apply here. Ahead of a riser, anytime we've got a branch, it's an end of main, as you can see in figure 4. We come down off from that end of main drip. We still have a leg for water to collect. We still have a blow down valve in our trap to go off from that. Again, the purpose of that, we know water is going to collect there when steam's changing direction at an end of main. So an end of main, or anytime you have a riser, very important to have a trap there because it will be a collection point for water. Again, the common sense will always tell you, keep thinking about what gravity does. Water is always at the lowest point. On branch lines, when you look at control valves, in the figure to the left there, we break the one rule that we had told you earlier about pitching with the flow. If you've got a control valve that's within 10 feet of a main line that's off from a branch like this, you're actually going to pitch it the other way because you want water to run back into that main line up above. When there's no steam pressure, you want to run back because there's drip traps to handle it. If it's more than 10 feet away, follow the rule, and that's to pitch with the flow. And anytime you're before a control valve and you're more than 10 feet away, notice that we have a trap. Always, 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 we would recommend a steam trap ahead of a control valve or a PRV. In addition, one other recommendation, depending on quality of steam, if you've got highly saturated steam coming out, if wetness has been a problem, we would also recommend in front of a control valve a separator. And so we want to keep that in mind. If you've got long runs, you've got wet steam problems, a separator is always healthy to have ahead of a control valve. The last thing you want to run through a control valve is very much water, any water, because it'll start to wire draw. But before that, we have a drip trap, as we would on a separator. We'd have a drip trap to try and dry that steam out before it goes through a control valve. Quickly on a PRV station, and for the essence of time, normally we would take a look here in the room at our station here, but we'll just look at this diagram. As you can see, our high pressure steam coming in the top. We come down and we have a drip trap, just as we discussed. Always a drip trap ahead of a PRV or a control valve station. And we have a blow down on that dirt leg to make sure we can blow that mud and what we call mud, call it mud leg, the dirt and crap out so the trap doesn't have to run that all through it. Going into the PRV, we have an isolation valve, we have a pressure gauge, and then we have a strainer and a blow down on the strainer. Same purpose as you want to blow down strainers because they will eventually plug and they're a nuisance if that doesn't happen. So an annual or semi-annual blow down of strainers is highly recommended. Then you have your PRV, you have a shutoff valve downstream. The purpose of the valve upstream and downstream is so you can service that PRV if it requires it's having trouble and your equipment downstream needs to be up and running. You can isolate that PRV, open the bypass valve up above, and can hand regulate so you can stay in operation while that valve is serviced. Isolation valves, the only recommendation we would make there is ball valves on steam are a really bad idea. And from there, it's up to you if you want to use gates there. The price is typically indicative of how the quality of that valve. And so again, we just recommend getting a good valve. There's nothing worse than trying to work in a PRV if those valves don't shut off tightly and you're getting steam leaking through. Your bypass valve up above should be a glove valve, something you can throttle. Again, a ball valve, absolutely not on the bypass. Go to a globe valve. Then downstream is the safety relief valve. Notice that where our steam is going back up, so we've got a riser. We're showing another drip trap at the bottom. Always, always, always. Okay, that's it's the lowest point of the system. Water's going to end up there. You want to be able to drain that off. So just real quickly, we've wrapped up with that. We're just showing this slide with the topics that have been talked about to date. There's something wrong with this diagram. And with your representative there with you, if you want to use this as a conversation piece of all the things we've talked about in the basics of steam, of steam trap operation, the two types, and of the piping, this is a good diagram to talk about. There's something wrong. See if you can identify what's wrong, the where and how. With this, we're going to turn it back over to Mitchell, who is going to cover water hammer.
Okay, so water hammer is a pressure or energy wave that's created when you have a fluid in motion undergo a sudden change in direction or speed. That should say velocity or momentum change. So water hammer is the biggest issue in really all steam systems. You can see some of the examples here of just what it can do to your equipment. We have a collapsed float on the top there. It could be from an F&T or a mechanical pump. The valves are completely blown out. It can easily crack trap bodies. In some cases, it can rupture piping. So really, it can damage anything in your steam system. And beyond that, it's also a big safety concern as well. If you have a steam explosion, you could have debris blown across a room that could hit someone. You've also got potentially live steam blowing out. So it's a big safety issue. You don't want to leave it unchecked. So we're going to go through the three types of water hammer, and we'll start with hydraulic shock. Now, hydraulic shock doesn't require a biphase system to occur in, and a biphase system is just where you have a mixture of a gas and a liquid. So in this case, it would be live or flash steam along with condensate. But again, hydraulic shock doesn't need a biphase system. It just needs a constant flowing column of water. And what happens is if you quickly shut a valve, that water that's moving is going to hit that valve, and it's going to create a pressure wave that's going to reflect backwards and hit whatever is behind it. And if that pressure wave hasn't dissipated, it'll keep reflecting back and forth until it's gone. And to give you a quick example here on the right, you have water moving at 10 feet per second, which is about 7 miles per hour, and you quickly shut a valve, it can create up to a 600 psi pressure wave. So to prevent hydraulic shock is really pretty simple. The main way to do it is just slowly opening and closing your valves. And also, if you have swing check valves, sometimes you can start to have issues with hydraulic shock when they close, and they can create pressure spikes on the discharge side. And so if you're noticing that issue, you might want to consider replacing them with silent check valves, also known as spring-guided check valves. Those tend to have much smaller pressure spikes when they close. The next type of water hammer is thermal shock. This does require a biphase system to occur. So if you have a relatively cool condensate line and you're putting steam into it, those steam bubbles that form are going to collapse. And when they collapse, you got to keep in mind that steam has a much greater volume than condensate. So only a little bit of condensate's left over, and the rest of it's just open volume that needs to be filled. And the condensate around it is going to fill it. So condensate rushes to the center of that steam bubble, and it's going to create a shock wave going out in all directions. And this might not result in the largest pressure wave, but over time, this can eat away at the inside of pipe walls, and it can rupture tube bundles and heat exchangers. It's typically identified by like a pinging sound, or sometimes people describe it as marbles are running through their piping. To prevent thermal shock, you want to replace filling steam traps, particularly steam traps that have failed open, because that's usually where you see it, is if a steam trap is blowing live steam into your condensate return line. Sometimes it's going to be inevitable that you'll have some steam going to a cool condensate line, so you might want to consider installing a sparge tube in those cases. Sparge tube just has small holes on the end of it, and as steam passes through it, it's going to cause that to break up into much smaller bubbles, so it'll be much smaller shock waves when they do collapse. Last type of water hammer is differential shock. This works on the difference in speed between steam and condensate. So if you imagine a pipe that's about halfway full of condensate, it's moving along, and you have steam running over the top of it, what will happen is, because the steam is moving so much faster, it creates little waves on that top layer of condensate. And if those waves get big enough, it'll fill the entire cross section of the pipe, creating a water seal. And steam won't be able to pass through that water seal, so downstream of it is going to drop in pressure. But your supply side, your supply steam, is going to push that water seal along through your pipe, and it's going to increase in speed, and it's going to also increase in mass because it's picking up more condensate that's in its way. And eventually that water seal will turn into a water slug, and it's going to move through your piping really fast and hit whatever is in its way. And you can pretty much think of it like a piston is moving through your pipe. Okay, so there's two main areas where you would typically see differential shock. One of them is your distribution lines. If you have poor insulation, or maybe it's not trapped properly, then you can start to have condensate building up and you just can't get rid of it quickly enough. You can start to see differential shock forming there. The other place is your condensate return lines. If, particularly if they're undersized, you'll have the same issue where there's not enough room and your steam is moving very quickly. So you start having water seals forming and start seeing differential shock there as well. And then sometimes what can happen is maybe you do size your condensate return lines correctly, but later down the line you install new equipment that increases your load, but you don't update your piping. So again, in that case, you would have undersized return lines leading to the same issues. Okay, and here's a demonstration of what differential shock looks like. So right here you can see you have some waves forming, and then there's your slug right there. Now in a live steam system, remember that that slug will be moving much, much faster, and it can cause a lot of damage. And I'll just fast forward this so you can see it under black light here. Okay, and that wraps up water hammer, and I'll pass it on to John.
Well, we've touched on 4 topics today. We've touched upon steam basics, steam trap operation, proper steam piping, and water hammer. Your local Armstrong representative is a great resource for more information on any of these topics. Please contact your Armstrong representative or ourselves if we can help you in the future. Thank you very much for your time today.